Welcome to Advanced Topics Midterm Review. I'm going to try to get all this in 15 minutes, but you could easily go past, so this might just be part one. We'll see. Number one, A and B, these are calculations which you can use using your EE key. Remember how we do that. If you would like to put in 2.50 times 10 to the 20th, you put in the number 2.50, hit second hand comma, and then enter your exponent, which would appear to be 2.50 E20. That's how the display would be. And you're going to times that by the other value. So 2 second hand comma negative 50, and we get an answer of either 5 E negative 30, which really means 5 times 10 to the negative 30th. 1B, 6 times 10 to the 23rd, which appears as 6.00 E23, divided by 2 times 10 to the negative 37, which appears as 2E negative 37. By the way, that's on the subtraction side, that's the negative sign. And we get an answer of 3E60, which really means 3 times 10 to the 60th. 2A and B, you are using dimensional analysis to convert to conversion factor, in other words. So I'm coming from this and I'm going to this. So I first set it up like this. Notice I've created a space for my conversion factor. I know clearly what I'm coming from and what I'm going to. What would my conversion factor look like? First of all, what I'm going to goes on top, and what I'm coming from goes downstairs. What are the relative values of deciliters and centiliters? Well, there are 10 to the 1 deciliters and 10 to the 2 centiliters. Of course, in normal numbers, that's 10 over 100. When calculated, we get an answer of 5 deciliters. In 2b, I'm converting from 6.25 times 10 to the negative 9 kilograms, and I'm converting to micrograms. I need a conversion factor. What are the relative values of kilograms and micrograms? First, I'm going to micrograms, so micrograms go on top, and the relative values are, well, there are 1 million micrograms in 1 gram, and there are 10 to the negative 3 kilograms in 1 gram. It'll be easier if I put this into my calculator using the EE key. So that's 6.25e negative 9 times, remember this is 1 times 10 to the 6, which is 1e6, divided by 1 times 10 to the negative 3, which is 1e negative 3, and I get an answer of, ta-da, 6.25 micrograms. 3 involve writing expanded electron configurations using SPDF. Oh yeah, what's that little triangle that's so useful in leading us through the buildup of the electron structure? Well, of course, give me an S, give me an SP, give me an SPD, give me an SPDF. Go cyclones. Also keep in mind that this is the first energy level. This is the second energy level. This is the third energy level. This is the fourth energy level, and we just go one more to the fifth energy level. We don't get any further than that. What are the maximum numbers of electrons that I can put in the S? 2. What's the max that I can put in the P? 6. What's the maximum that I can put in the D? 10. And the max in the F, even though we never get there, is 14. Now remember, we're going to follow a diagonal path. First, we fill up the 1s, and then we fill up the 2s. We fill up the 2p, and then the 3s. We then fill up the 3p, the 4s. Then we go and we can fill up the 3d, and maybe we'll get to 1, which goes to a 4p, and the furthest we'll go is to the 5s. 3a. Argon has an atomic number of 18, means there are 18 electrons to place. The first 2 go in the 1s2. The second go in the 2s2. The next 6 go in the 2p6. Notice that's 10. The next 2 go in the 3s. And that leaves 6, and the remaining 6 go in the 3p6. Chromium is atomic number 24. The first 2 go in the 1s. The second 2 go in the 2s. The next 6 go in the 2p. The next 2 go in the 3s. The next 6 go in the 3p. That leaves us with 6 more. We now get to the 4s. I put 2 there. And now notice I get to the 3d. And I can put 4 there. But you've got to keep in mind that chromium is one of the 2 exceptions, copper being the other. And so you have to make a slight alteration to get full credit. One of the electrons actually relocates to be in the 3d. So you have to make this 4s1, 3d5. So here is your final, complete, perfect answer. But I think you've begun to notice that once you get this in, you realize it always starts the same way. So I don't have to go through copper laboriously. I know argon, the first 18, is going to also be the foundation of copper. So let's just bring argon's configuration down. Boop! And notice atomic number 29, there are 29 electrons to place. I've placed 18 so far. Let's keep going. I go to the 4s now, 4s2, which brings me to 20. I now go to the 3d, and I need 9 more. So that's 3d9. Like chromium, this is also an exceptional case. One of those electrons makes a little trip from the s to the 4s to the 3d. So your final answer has to be altered for full credit to 4s1, 3d10, giving you a final answer that is circled here in green. Not too bad. Question 4, the triple point. Every student loves a triple point, recall. This is a relating of temperature and pressure and how that affects the phase and phase changes of a given substance. What I would recommend you first do is you always have 3 regions. Remember here, C has got to be a solid region. Why? Really high pressure and really low temperature. By contrast, if I increase the temperature and I really decrease the pressure, which I'm doing here, I'm going to get a gas. And of course, what's sandwiched in between? Liquid. Okay, with that set up, let's do A. What is the triple point temperature? Well, the triple point is that point which touches all 3 phases. It's right there. It has to be a pressure of 6 atmospheres at a temperature roughly of negative 15 degrees Celsius. Please don't leave out the negative. We can't give you credit for that. B, what phase change occurs from region C to region B? Well, we've labeled the phases. So the phase change is just solid to liquid. The name of it is melting, of course. Finally, what is the name of the phase change that occurs as the pressure is decreased from 30 atmospheres to 1 atmosphere at negative 100? Well, let's take a moment. Let's not rush into it. Let's find 30. Here's 30. And let's find 1. And we're going to be making a trip at negative 100, which is around here. So the trip is going to take us from here to here. We crossed that line from solid to gas. Solid to gas, that is called sublimation. Exactly, sublimation. Again, it's the question everybody loves. From the question everyone loves to the question that everybody hates, at least Mr. Byrne. A little shout out to Mr. Byrne. We were talking, students don't like calorimetry. This is heat transfer. Remember, we summarize it by saying that the energy lost by one part of the system is gained by another part of the system. So let me do a little sketch of the system here. Well, both samples are samples of water. You happen to be mixing 800 grams of rather hot water. So let's label that. That's right here. As I said, we have 800 grams of rather warm water. Of course, water is always 4.18 specific heat capacity. And the initial temperature was 95 degrees Celsius. And we're mixing it with water, which is still water, so it's still 4.18 joules per degree joules gram degree Celsius. The mass we don't know. So the mass is what we're solving for in the problem. The initial temperature is 30 degrees of the water. Now, once they mix, you notice that the final temperature of both systems, or it's one system, of both parts of the system is 45. Now, since both are changing temperature, we're going to use MC delta T for both Q's. So M times C times delta T for the hot, hot, hot. M times C times delta T for the cold, cold, cold. Let's plug in what we know. I put in the mass of the hot water, specific heat of water. Notice that I had a decrease from 95 to 45. That means there was a negative 50-degree decrease. That means that those negatives cancel out. We're solving for the mass of the cool water. It's 4.18 specific heat. Notice that the cool water went from 30 up to 45. That was a increase, a positive change of 15 degrees Celsius. So we're just going to solve for x. When we do, we get 2670 grams of water. Moving right along to number 6. A photon of light has a frequency of 6.0 times 10 to the 17. Frequency is F, or is also Greek symbol for frequency. So that's something we know. Recall there are two formulas for light. Wavelength is related to frequency through the speed of light equals wavelength times frequency. So sorry, I reversed this here. It's actually a Chinese letter. Speed of light is always given to you as 3.00 times 10 to the 8th meters per second. The wavelength is what we're looking for, so we just call that wavelength. And the frequency of this beam of light, this ray of light, this photon of light, is 6 times 10 to the 17. When I solve for wavelength, I get 5 times 10 to the negative 10 cycles per second. Of course, your calculator might say 5e minus 10, same exact value. B, calculate the energy of this photon. So we're still using the same frequency. But there's another formula that relates energy to frequency. Energy equals something called Planck's constant times frequency. Planck's constant is given to you as 6.63 times 10 to the negative 34 joules seconds. The frequency remains, as I said, 6.0 times 10 to the negative, to the 17th cycles per second. Oh, by the way, I'm sorry, wavelength is meters. Sorry about that. That should have been meters. When I do the math here, I get 3.98 times 10 to the negative 16 joules of energy. Very small amount. It's only one photon of light. As I only have a little under 2 minutes left, although I probably get to this question if I work very carefully, I'm going to postpone this to part 2. So you've been watching part 1. This is the end of part 1. Please join me for part 2 of the Advanced Topics Midterm Review. See you on YouTube.